Okay, good afternoon, everyone, those present here and those connected remotely. It's a great pleasure to have you here for a very special guest invited today. The topic of today's colloquium is devoted to the climate crisis, which we know is a topic of hot debate because of its implications for the daily life of everybody and for economy, but also because it's subject of strong political debates, often with fake information, fake news, and also populistic currents. So we have felt the need of participating consciously to this debate, going a couple of steps back and calling the foundations of the scientific work based on which we have our current understanding of the problem. So we decided to invite here one of the leading experts on the scientific studies beyond the foundations of climate modeling and understanding. So it's a great pleasure to welcome here Professor Thomas Stocker from Bern University. That is working on climate dynamics and paleoclimatic modeling and reconstruction, mostly based on ice sampling in Antarctica, but going well beyond that. And he will illustrate today to us the usage of the data collected from ice cores in the constructions of modeling was comparison with existing data also allows to make predictions for the future. Now, from the year 2008 to 2015, which is a very long time, he has been co-chairing the Working Group 1 of the Intergovernmental Panel on Climate Change, also called IPCC. And the report from this working group in September of 2013 formed the scientific basis of the Paris Accord of 2015. Now, he has received a numerous number of awards. I don't even attempt to mention it, but the most recent is the BBVA Frontiers of Knowledge Award of the year 2024. He is also a member of many prestigious academies, the list of which will be failing, but among those we can mention also the Accademia dei Lincei in Italy, and not to keep you long, I would like to give the stage to him. Thank you very much for being here today.
Well, thank you very much for this kind introduction, and thank you for the invitation to come here to the University of Padova to tell you a little bit in the next 45 minutes about climate physics. Maybe you think climate science is located in geology. Yes, it is, but it's also located in physics. And at our university, at the University of Bern, we do climate science or climate-related research in actually 5 different faculties. The latest addition to our academic activity at the University of Bern in this topic is medicine. So we will establish a chair in climate and health. So just to say, this is a very interdisciplinary topic. And so many people think they can engage in a reasonable discussion about climate and climate change. But I would like to argue that physics has a special place in this discussion because we measure and we understand and we test hypotheses. We go back to the data. We look in the past what happened to the system Earth, to this dynamical system. And based on that fundament of knowledge, we're also able to make reasonable projections of possible future climate change. Now, the most important diagram in our discussion is this one. I'm sure you all have seen this. It's the ultra-precise measurement of the most important greenhouse gas in the atmosphere after water vapor. Water vapor is the most important one. but it's part of the natural cycle. We will look at that in a minute. This is carbon dioxide, and it's established fact that the reason for this increase that you see happening since 1958 is due to the combustion of fossil fuels, coal, oil, gas, and there is also a contribution from global deforestation and land use change. What you also see on this curve is actually quite a nice feature that is unique to our planet. These are the annual variations of carbon dioxide that you see here. They are a testimony to the precision of these measurements, and they are also caused by the respiration and the breathing of the terrestrial vegetation. So in spring, when the leaves are growing, carbon dioxide is absorbed from the atmosphere, and in winter it's respired again. And these are the small wiggles that you see in very high regularity. It's the signature, the fingerprint of the global carbon cycle. Now today we are here, 2024. It's 35% higher since 1958 based on these measurements, and it's 54% higher than pre-industrial. 1750, sort of a year where we can say the combustion of fossil fuel has started in sort of a global scale, leaving a trace in the atmosphere. Now, you may wonder why we can actually affirm that this is 54% higher than 1750. Here come the ice cores from Antarctica, where we have a natural climate archive of greenhouse gases. You see here in these little photographs at the top here, you see a sample of an ice core cut and lit from behind. You see these speckles. These are air bubbles, and these air bubbles obviously contain nitrogen, consist of nitrogen, oxygen, but also of traces of greenhouse gases. And it's these greenhouse gases that we measure at the University of Bern in Switzerland in very high precision. Knowing how old the ice is, you can then reconstruct past concentrations of carbon dioxide and methane incidentally, and nitrous oxide incidentally, and many, many other species from these ice core samples. And what you see here is really the effort of about 60 years of research and development, with many, many students, postdocs, and scientists working towards these time series that you see here in blue. It's also the result of a high degree of international collaboration. Drilling an ice core in Antarctica, not a single country can do that. Nowadays, you need consortia, and in our case, it was 2 big European projects where 10 nations from Europe have participated. In fact, at the Italian-French permanent station of Dome Concordia, where this ice core was drilled, and an ice core that goes back 800,000 years. That is at the bottom of this core, about 3 kilometers below the ice surface. The ice has an age of about 800,000 years. And of that 3-kilometer long ice core, many scientists have now cut that ice core in pieces and sampled very carefully for different climate indicators, foremost the greenhouse gases. What you see here, 800,000 years before the present, starts over here. Time goes from left to right. Today is here. And you see CO2 was never constant in the atmosphere. There were natural variations between a well-defined range of about 180 ppm to about 300 ppm max. But today, we are far beyond that natural range, and it's not astonishing because we have emitted so much carbon dioxide into the atmosphere that we are outside of the natural range that is established by an equilibrium of the carbon reservoir between the atmosphere, the ocean, and the vegetation. What you also see, if you count the maxima and the minima, that we have a sequence of about 8 cycles. These are the well-known ice age cycles. The last ice age came to an end about 20,000 years ago. That's just about here, where about 2/3 of Switzerland was covered in alpine ice. And you also know about the Piedmont Glacier, province Piedmont, came down from the Alps far into northern Italy. That was the condition about 20,000 years ago. And you see that this condition, if carbon dioxide is a measure for where these ice ages occur and when they occur, that occurred about 8 times on this time axis. We know from marine sediments that ice ages go much, much further back, about 3 million years, where we can trace these ice ages in all marine sediments. And in fact, marine sediments are one indicator that allows us to actually date this ice core, but we have a few others. Well, since I'm here with a physical audience, I thought it would be useful to give you a little bit of a flavor what we teach our students when we sort of acquaint them with the basics of climate and climate change. And we do that with a very simple toy model, just not to explain the world, but to give you a flavor what is relevant and what is important in the climate system. We think of it as a point in space that radiates energy away that is received by the sun, our energy source. You see that we can actually formulate an energy balance equation. This is really trivial, just one quantity, the global energy, that changes as a function of time, and it's simply a balance between the source of energy and the sink of energy at this planet. You see here Stefan Boltzmann's law. You see an emissivity here with the epsilon. You see the radius of the Earth. You see the solar constant, and you see the reflectivity of the Earth as a whole. These are all planetary scale parameters that are used to describe but the most fundamental changes in the climate system. Now, there's a lot of debate about the greenhouse effect, and in fact, this is a misleading term because we think when we hear greenhouse effect, we think of perhaps a glass roof, like the atmosphere could be a glass roof, and somehow this leads to a warming of the planet. Well, for the broader public, this is probably the shortcut explanation, but in front of this audience, I want to be a little bit more precise. So, of course, when you talk about the greenhouse effect, you have to talk about wavelengths of radiation. The visible is between 400 and 700 nanometers, but there is also infrared radiation. That is the radiation where some molecules that are present in the atmosphere, and it's trace molecules, it's the water molecules, the carbon dioxide and the methane molecules are the most important ones, absorb radiation. So they have absorption bands. This is a consequence of quantum mechanics, so no discussion there. And we know that there are several bands between 8 and 12 micrometers of wavelengths. And in essence, if you look from space to the Earth in the visible band, you see the Earth like that. That's the blue marble we are all familiar with from the pictures and the photographs from the early 1970s, where astronauts have caught a glimpse of our planet in this way. But you could also ask, well, how would I look at the Earth if I had only an infrared sensitive eye? And that's more or less the picture that you see here. It's very hard to see continental outlines, which is already an important indicator as to how large your line of vision actually is and how deep that line of vision goes towards the surface of the Earth. And that's precisely the origin of the natural greenhouse effect. Now we know that the atmosphere is stably stratified made evident through the change in temperature. That's the dependence and the cooling as you go up. We have all experienced that at about 6.5 degrees Celsius per kilometer of altitude, temperature decreases. So this is a sketch of that temperature profile through the air. And you see here that's in the visible band. If we look from outside, we can actually see the Earth's surface. The Earth's atmosphere is transparent to some extent. Of course, you cannot see through the clouds, but where there are no clouds, where there's very little water vapor, greenhouse gas, you see the continents. Now, that's the situation with no greenhouse gases. With greenhouse gases, you're essentially looking into a dirty pond. The atmosphere has substances in it that absorb the visible and the infrared light, and therefore, your line of vision is not as deep as before. In fact, mean depth of vision is about 5 kilometers, and that's sketched here. At 5 kilometers, we have a mean annual temperature of about minus 18 degrees. And it happens that this minus 18 degrees is the mean radiation temperature to space. So if you look at the planet and look at the spectrum of radiation that you receive from the planet, this is the equivalent temperature from Stefan Boltzmann's law. And that corresponds to about 238 watts per square meter. That's the equilibrium temperature. We call that equilibrium temperature. But you're all aware that our mean surface temperature is not minus 18 degrees. That would be an inhabitable planet. The mean surface temperature is about 14 degrees. And so there is an effect here that increases the surface temperature by a large amount. Now, what happens if we add greenhouse gases to the atmosphere? If we increase the concentration of greenhouse gases, think about the dirty pond. We increase the dust or whatever, the sludge in the dirty pond. You don't see deep into the pond anymore. So our line of vision actually goes up if we increase the greenhouse gases. So let's increase the greenhouse gases. Our line of vision is shorter, goes to lesser depth, about 500 meters is the estimate, that the mean radiative temperature is higher up if we have a double concentration of carbon dioxide with positive feedbacks added. And so you see, because we are in this very stably stratified atmosphere, that's really a very stable process that is hard to disturb, we radiate away at minus 21.6 degrees Celsius, and that means we have only 230 watts per square meter. So the planet is losing about 8 watts per square meter on average, less than before. Well, what does that mean? That means that the atmosphere below will heat up. That should come here. Let's see. Yeah, it will heat up until that magic temperature of minus 18.6 degrees is reached. Why is that? Because that is determined by the incoming solar radiation, and that has not changed. Okay? And so this leads to an increase of the temperature. And because that stratification is, as you know, determined by the adiabatic processes in the atmosphere, the barometric formula, you see that the whole atmosphere actually gets warmer. It's not just the surface. It's the whole troposphere that gets warmer because we are radiating away less energy. All right, and that leads then, by a doubling of carbon dioxide, to about a warming of 3 degrees throughout the entire troposphere. Well, this is still a simplified way of explanation, but it's much more physical than the glass rooftop that causes a warming. Now, based on the previous argument, and I see you have all followed attentively, you can now for yourself respond to the following question. If this is the process that warms the atmosphere, what would happen in the stratosphere? Well, the stratosphere is another beast. In the stratosphere, because of chemical compounds, foremost ozone, we don't have a decrease of temperature with altitude, but we have an increase of temperature with altitude. It's about 1 degree Celsius per kilometer. Okay, that's the middle stratosphere, above about 10, 12 kilometers. So a normal temperature profile, the so-called standard atmosphere, if you have soundings all over the place and you average, that's the standard atmosphere in terms of temperature. You have warm surface temperatures. You go up to about 10 kilometers. It cools down. Then you have a layer of more or less constant temperature. And from 20 kilometers onwards, it increases again, the temperature. That's the middle stratosphere. Now, based on that argument before, what would happen? Well, this is what happens. Because we have an inverse gradient in the stratosphere, we are actually losing too much radiation when greenhouse gas concentrations increase. That means we need to cool down the stratosphere to reach radiative equilibrium again. And so that's sort of what's happening. That's the prediction of this very simple, basic explanation of the planetary greenhouse effect. We'll have a stratospheric cooling, and we will have a tropospheric warming. What I explained to you was already known in the 1960s. Okay? So scientists have known that before, but today we can actually inquire whether the measurements show that fingerprint that we predict. And here is the temperature trend as is reconstructed from global measurements between 2002 and 2019, given in degrees Celsius per decade. And you can see here, this is just showing the stratosphere. There is a warming up to about 15 kilometers. There is, first of all, a latitudinal structure to the temperature profile. That's yet another story. The next level of complexity from 70 degrees south to 70 degrees north. But then above, we measure a cooling, and that cooling even increases if you go up from 20 to 25 kilometers. Left is observation. Right is soundings from various different sensors. And you see here very clearly the signature to about 200 millibars of pressure. That's about 15 kilometers. We have a warming, and above there is a cooling. Now, climate models. Some people say, well, climate models can't really do anything. They are just statistical things that are tuned to the present climate. Well, no, these are dynamical models that essentially are based on classical physics and hydrodynamics or geophysical fluid dynamics. And you can see here the temperature change simulated by a whole suite of climate models. You see here the mean. temperature change between the 1990s and the end of the 21st century. So we are looking at a time where we would achieve 2 times CO2 in the atmosphere for that scenario. And these models actually simulate just what I said, that is a warming in the troposphere and a cooling in the stratosphere, with an amplified warming in the northern hemisphere high latitude. So it's observations, it's fundamental theory, and it's models. Let's go on here with a little bit of equations. I'm actually quite happy because in public talks I can never show these, so I'm really enjoying myself here. You remember this equation. It's the simple energy balance. What comes in, something goes out, and the difference leads to a temperature increase. Now you can actually generalize this energy balance if you say, well, there are several terms that are responsible for sources and sinks, and they all may depend on temperature. For example, the content of water vapor in the atmosphere, or the coverage of clouds, or the ocean circulation, whatever. And you can formalize that in this way, the left-hand side, dEt by dt by d time, plus on the other side a sum of different factors depending on time, plus an additional energy amount that is added to the system. You will see what that is in a minute. We linearize this equation, and what we can then do is to say, well, the time change of the perturbation of that temperature is a sum of the derivatives of these 3 different processes that I have chosen as a function of temperature times the temperature perturbation plus that additional energy that we are adding to the system. We will turn to that in a minute. We call these derivatives of the processes A, B, C, or even more processes derived by differentiated with respect to temperature. We call these feedback parameters, and these feedback parameters are additive. So different feedbacks add to one another, and we can now inquire our global climate models how these different feedbacks play out in terms of quantitative numbers. We have the Planck feedback, which is just the gray body radiation. You can actually work that out on a piece of paper. And you see these global climate models, they actually agree very well with that Planck feedback. It's about 3.3 watts per square meter per Kelvin. Then the water vapor and lapse rate feedback is also quite nicely constrained by these models. There are other feedbacks, as you can imagine, the clouds, which have a spatial variability, both horizontal and vertical, but also a variability in terms of the nature of the clouds. We have quite a spread of that feedback parameter, which then translate into the spread of the total feedback parameter, which is the sum of all of them. And it's useful to see how big that sum is. It's minus 1.2 watts per square meter and Kelvin. That's sort of an estimate of that feedback parameter. And if we know that number now, we can actually formulate that perturbed energy balance and then solve for it in this point climate model. And you see there are 2 things that determine the perturbation. There is a transient term here that actually either increases in time or decreases in time. Now, aren't we happy that this lambda is negative? So whatever the perturbation is, it fades away exponentially in time. But there is the second term that is proportional to 1 over lambda and to delta Q, and that is the so-called radiative forcing. That's where the greenhouse gases come in. So if we have a doubling of greenhouse gases, there will be a watts per square meter on that delta Q. You multiply that by 1 over lambda, and you get a delta temperature. That's where the 3 degrees comes from when you double the carbon dioxide concentration. I've indicated that here. That's the equilibrium. So this term fades away with T to infinity, and you're left with an equilibrium warming of about 3 degrees. Okay? We go here a little bit rapidly. This is the so-called climate sensitivity, or the equilibrium climate sensitivity, estimated based on this point model at about 3 degrees Celsius. Now going back to IPCC, this Intergovernmental Panel on Climate Change, which has the mandate to assess what the climate science knows about both the natural and the anthropogenic climate change. And they existed since 1988, have by now published 6 voluminous assessment reports, heavily reviewed. Everybody had a voice, and in the end, we come up with a consensus. One of the items here where consensus has to be found is equilibrium climate sensitivity. In the report that I co-chaired in 2013, we identified a likely range from 1.5 to 4.5 degrees Celsius. We said it's extremely unlikely that climate sensitivity is very small. In other words, it's extremely unlikely that an increase of CO2 would have no effect. And it's also very unlikely that an increase of CO2 would have a tremendous effect. So the climate sensitivity is very unlikely to be larger than 6 degrees. Now, 8 years later, in the 6th and latest assessment report, this was somewhat revised. The whole range, the so-called very likely range, was shifted by about ½ degree upwards. The likely range is within that very likely range, so it's a bit wider. A bit narrower, and the best estimate is about 3 degrees Celsius. And here we come now to some very familiar figures. At least the third person here, Giorgio Parisi, you know, an Italian scientist who actually has the doctoris honoris causa of this university. He got the Nobel Prize in Physics in 2001 and shared it with 2 climate modelers. We were all very surprised. Well, not really. We knew that it was overdue, but still very surprised that these 2 highly respected colleagues on the left, Syukuro Manabe, and in the middle, in the center, Klaus Hasselmann. Manabe is from Princeton University, and Klaus Hasselmann was the founding director of the Max Planck Institute for Meteorology in Hamburg. The 3 shared this Nobel Prize in Physics, not in equal parts, because Giorgio Parisi actually had an achievement that is much more fundamental than the achievements, which are also very important, of the climate modelers. And so that is why Giorgio got 50% of the Nobel Prize in Physics, and the other one shared 25%. But these are details the public doesn't really remember. So they got their prize and their recognition for groundbreaking contributions to our understanding of complex physical systems. Manabe and Hasselmann for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. And Parisi, and I'm sure you had lectures here explaining what his contribution was for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scale. Now, I will focus on the contribution first of Syukuro Manabe, and then very briefly on Klaus Hasselmann's achievement that led to the Nobel Prize in Physics. Well, I mentioned in the mid-1960s, essentially the physics of the atmosphere was already understood. And this is a paper from 1967 that he published together with a colleague, where he investigated in a column model. So he collapsed the entire complex atmosphere in just one dimension, from the surface up to the stratosphere. and investigated the dependence of the thermal equilibrium to changes in temperature. And he could identify here, first of all, he could model a steady state atmosphere in this radiative convective model with a CO2 concentration of 300 ppm. That was sort of the concentration in the early 20th century. You see here the troposphere that shows a cooling as you go up, then more or less steady temperature profile up to about 25 kilometers, and then an increasing temperature there. So he could actually simulate quantitatively based on thermodynamics and convection parameterization the structure of the atmosphere. What he then did was he increased the concentration of the greenhouse gas, and what he found, and I've highlighted that for you so you see it a bit better, in this age people only published black and white. He could indeed, by an increase of carbon dioxide to the double level, to 600 ppm, identify a warming in the troposphere and a cooling in the stratosphere at 600 ppm. So, great achievement, recognized only in 2021. But that achievement was the basis of the vertical formulation in climate models of all generations to follow. Manabe was a very targeted person. He had high ambition, and he then went on, having understood the vertical structure of the atmosphere, to extend that knowledge in the horizontal, and he came up with the first global climate model. And look how simplified that looks like. It's a planet that consists 30% of, it's actually only a sector because of computational constraints. About 50% is ocean and the other 50% is land. And he was really a very talented scientist who knew precisely the limits of interpretability of that simplified model. And so the results that he obtained are still valid today. That's really the astonishing thing. A couple of years later, he was not happy. He teamed up with Kirk Bryan, an oceanographer or an ocean modeler, and you see here already some continental outlines, both in the atmosphere with topography and the ocean with ocean basin, which is changing horizontally, depends on latitude and longitude. And he coupled these two components of the climate system together. That's the first coupled model. And with that coupled model, he made another prediction. He made the prediction in 1989 how the fingerprint of the atmospheric temperature change in latitude would actually change in time when carbon dioxide slowly increases over a period of about 100 years. This was an artificial experiment, but he wanted to know what happens. How is the heat distributed in terms and as a function of latitude? You see this in this so-called Hofmüller diagram, where you go on the vertical axis from 90 south to 90 north. So you go across a meridian, you plot the zonal average temperature change as a function of time here horizontally from 0 to 95 years. Again, a black and white figure. You see that the warming occurs slowly throughout these 50 years, but with an enhancement of the warming in the northern hemisphere. You see the fastest warming occurs at the highest northern latitude, and the slowest warming occurs between 50 south and 70 south. Why is that? Well, it's kind of obvious, because in the southern latitudes you have ocean, very high heat capacity, same input of energy, small delta T. In the northern hemisphere you have comparatively less ocean, so less heat capacity for the same amount of energy, more delta T. And in fact, I've asked my PhD student a couple of years ago, just after that Nobel Prize, in fact, could you download the latest database of temperature readings from 80 south to 80 north as a function of time? All he got from 1950 to 2020, and plot the change in temperature. And, you know, this is fantastic. That's what well, it's not fantastic because it shows global warming, but it's fantastic what Manabe and Brian have predicted in 1989 already. So this is what we observe today. Now, to Klaus Hasselmann, a few words also. He's also a theoretician, so he was much more theoretical, and he actually built an ocean model for climate studies. And that's for us very important because the models that Manabe built were very expensive and they could be integrated for only a couple of 100 years. Hasselmann's goal was to have a simplified ocean model with dynamics that is able to integrate over thousands of years. And so he formulated equations. You see here the conservation of momentum as the first equation on a rotating planet. Then you see the vertical equation, and you see a conservation equation for temperature and salinity. And that efficient ocean model actually allowed him to be the first who has added tracers or other substances into the ocean. The most important substance you can imagine is carbon dioxide. So he coupled the carbon cycle, the global carbon cycle, to the ocean circulation to address the question how much carbon that we emit into the atmosphere is actually absorbed by the ocean. And this ocean model I want to show you because here there is a connection to my predecessor at the University of Bern, Hans Oeschger. What they simulated was a specific part of the carbon cycle, and that is the radionuclide carbon-14, radiocarbon. This is a natural nuclide which is used to date water in the ocean. And you can see here a transect from 90 south to 90 north through the Pacific Ocean. You see this here in this little map. And the contours here indicate the concentration of radiocarbon. Where you have very little concentration, these are the high negative numbers. That's a sort of a depletion measure that is applied here. You have very old water masses. And this model simulates the oldest water around the equator at depths between 2 and 3 kilometers. That's sort of this area with high values at the surface where you exchange the radiocarbon with the atmosphere. Radiocarbon is continually produced in the stratosphere. That's why it's high at the surface of the ocean. Well, Hans Oeschger actually in 1959, my predecessor, has measured this low radioactivity in the Pacific Ocean at these locations, and the agreement is just astounding. What is also important for the question, can we actually quantitatively make a link between the increase of carbon dioxide and changes that we see in the climate system, not only global mean temperature, but also perhaps sea ice or other quantities that you would like to identify and quantify how much of the change is due to the anthropogenic forcing, is the so-called detection and attribution science. And Klaus Hasselmann is really the founder of that science that is enormously important. And you can see just an excerpt from one of his papers in the early 90s. He was doing really highly theoretical work, which now is routinely applied when you would like to answer a question, well, how much of the change that we see, for example, the increase of temperature in Veneto over the last 50 years is due to the increase in global concentration of carbon dioxide. And here we come to the Intergovernmental Panel on Climate Change. I have only a few minutes left. 1990 was the first report being published. This report was in preparation of the Earth Summit in Rio, where the politicians and policymakers wanted to know, what do we really know about climate change, also the anthropogenic. No statement on detection attribution. Very interesting. Science wasn't ready to do this detection attribution statement. 1995, already a statement that is sort of kind of vague. The balance of evidence suggests a discernible human influence on global climate. Nothing more specific. 2001, there is new and stronger evidence that most of the warming observed over the last 50 years is attributable to human activities. That is already a time where there were lots of scientific activities combining model and observation to do this detection and attribution technique. 2007, more specific, and in our report 2013, we said it is extremely likely, that is 95%, that human influence has been the dominant cause of the observed warming since the mid-20th century. And because we were always criticized to use too complicated language for the public, we said the following sentence: human influence on the climate system is clear. Now imagine this sentence was stated by the scientists based on the science. The policymakers actually accepted that sentence in consensus. It took me only 20 minutes to read it out, ask the audience any intervention, and nobody intervened because the science was actually very obvious and robust. So this is now a statement that is a statement of 195 countries. It's a UN document. Anyways, I'm quite happy about that. And in 2021, we have said it's unequivocal that human influence has warmed the atmosphere, ocean, and land. You see how these statements become firmer and firmer, more robust, more focused. Here we say the same thing for atmosphere, land, and ocean. Ocean being the component in the climate system where the latest measurements come from, but because of the high capacity, heat capacity of the ocean, these measurements are also very difficult. Now let's turn back to the models. People say, well, models, we don't trust them. Still in 2024, people say we don't trust the models. Well, ask the same question for the models that were available in 1970 and in 1975. These were the projections at that time up to the year 2010. Then in the next report, 1993, these were more simulation. You see already natural variability coming into these simulations. Then in successive IPCC report, you see these projections where we said from 1990 to about 2020, there is a warming between about 0.6 and 1 degrees. that's the data before, so that's just combined. You see what IPCC said. These are, the red ones are the primary publications. IPCC has this bluish curves here for different scenarios and different reports. And if we overlay that with the observations for global mean temperature, these projections have been reliable already almost 50 years ago. All right, so now let's come to today, and then I am closing quickly. These are the sources of carbon dioxide emissions since the 1850s, since industrialization. You see land use changes. The yellow band hasn't changed a lot. There were phases where the land use change went down, but oil and coal and also gas have increased steadily. There are projections around for the end of the 21st century, different scenarios. We have to work with scenarios. We cannot predict 2100. That is dependent on how much we emit. Heating above 2 degrees Celsius is to be avoided, as the Paris Agreement says, since 2015. Whether we will manage is a different question. But what does it mean? It means that we are today using models that are coupled of that fine grain, and these models predict a warming depending on the scenario from about 1 degree more relative to today to up to 5 degree more relative to today. Sea ice goes back in the northern hemisphere. Global mean sea level rise is also increasing because of the expansion of the ocean water due to the warming, plus the melting of glaciers and the polar ice sheets. Greenland, for example, just a number to remember for you, Greenland is losing a cubic kilometer of ice every day. That we know from fantastic gravity satellite measurements that essentially measure on a weekly basis the differential gravitational pull of 2 satellites that flow over Greenland and Antarctica. I think I can go quickly here. These climate models have become so sophisticated that we can now make reasonable guesses or projections as to the regional distribution of temperature, the regional distribution of precipitation, not on a point-by-point basis, not on a provincial basis in Italy, but on a large-scale basis. These models can provide robust results. And so we say every degree of global warming accentuates regional changes. You can see the drying and the wettening of the atmosphere in the lower panel row become more intensive depending on the warming of 1.5, 2, or 4 degrees Celsius relative to pre-industrial. And so I am mindful of the clock, and I would like actually to close with a very short consideration of what's happening to extreme events, because it's at the end of the day, the extreme events that cost a lot of money. Adaptation to it costs a lot of money. I'm showing just the heat waves here, frequency of heat waves. What used to be a 1 in 50-year event under almost no global warming has become a 1 in 10-year event. You see here very faint 50 dots. These are 50 dots, and 1 dot colored means 1 times a heat wave in 50 years. Now with 1 degree warming, we have a 1 in 10-year event. Out of the 50 years, about 8 years will be extreme hot years at the warming of 1.5. And with every 1/10 of a degree that temperature, global mean temperature, is increasing, the amount of, or the frequency of extreme events is increasing many folds. This is obvious also if you think about a Gaussian distribution. You look at the leftmost 5%, you move a little bit your Gaussian, and you answer the question, what's the change in percentage per change in mean? And with 4 degrees, we are at the new normal. About 39 times out of 50 years, we will have a heat wave that today is called a 1 in 10-year event, and before, that's the statistics of the insurance companies, is still a 1 in 50-year event. So, take-home messages here. Greenhouse gas concentrations have increased. That's a fact. The science from climate physics, ice core analysis, paleoclimate science, and that increase has mainly occurred during the Industrial Revolution. The raise of the level of the effective radiative loss to space is really the perturbed greenhouse effect that leads to a warming in the troposphere and a cooling in the stratosphere. And the measured changes in the last 50 years in many, many components of the climate system are attributed, that's the detection and attribution science, to the emission of greenhouse gases and aerosol. Now, with every half a degree of warming, extreme events will rapidly increase, and that's why it's so important. Not to say, well, it's just half a degree or something. Every half degree actually counts. And I'm just reiterating a statement here that we also passed in the 2013 report of the IPCC to all the policymakers. Limiting climate change requires rapid and sustained reductions in greenhouse gas emissions. Well, when that statement was accepted, I was accused of being a climate activist because this statement reads, we need to limit greenhouse gas emissions to protect climate. I said, well, guys, please read the English carefully. What you read here, if you have followed your English lessons, that's a conditional. If you decide you want to limit climate change, then the science tells you that you have to reduce substantially and sustainably the greenhouse gas emissions. And in a nutshell, climate change is physics. Thank you very much.
Okay, thank you very much for this very interesting colloquium and also for the physics explanations that you provided us. I would like to open now for discussions and questions. Particularly students are warmly encouraged to participate.
Thanks a lot for your nice talk. At the beginning, well, and also later, you have shown this equation in which you have the temperature that is a function of time. So it means that we are out of equilibrium somehow. And so there is the derivative of the temperature with respect to time. And so are there some constraints that make this model reliable? That's the question.
This is only a pedagogical model. It's not a model that anybody would rely on to predict something. But it's a model that, or a consideration that gives you the most basic physical explanation, which is also correct, and which is contained in a more sophisticated formulation of how the vertical temperature profile reacts to changes in the greenhouse gas concentration. So that model of Manabe, for example, in 1967 actually calculated the radiative balance in many layers, successive layers, throughout the vertical atmosphere. So whatever radiation came from layer n-1 was then calculated and added to whatever comes from layer n, and so you go up and you sum essentially the absorption of radiative energy at each layer, depending on the concentration that is present at that altitude of the atmosphere. So I think it's really just a pedagogical mean for lectures and for students to provide a more accurate model of how the greenhouse effect works, a model that does not rely on this glass ceiling where you take one point somewhere in the atmosphere and say, oh, parts of the radiation is reflected back somehow to Earth and half of it is escaping to the atmosphere. So it's actually much better because it depends on that vertical gradient of temperature, which we are all very familiar with and is a very strong constraint, a very strong thermodynamic constraint of the atmosphere.
I have two questions. The first one is there any foreseen effect of the stratospheric cooling on life on Earth, like not just human life, but also Earth in general? And the second question would be a more broader one, which is what's next in climate modeling and in this field?
Yeah. Well, thank you very much. Stratospheric cooling, of course, and that's now beyond my area of expertise. The stratosphere is a part of the atmosphere where many, many chemical reactions take place. So you have all kinds of trace gases up in the stratosphere. You have radicals in the stratosphere that participate all in very complex chemical reactions. All we know, for example, is the ozone problem. And the stratosphere is really a hot pot of chemical reactions. And so each chemical reaction you can describe by equilibrium constants. And we all know from Boltzmann's law that these equilibrium constants are very strongly temperature dependent. Now, if you change the temperature, you change the kinetics of these individual reactions, which then has the potential, and here I'm really not being able to provide you with firm results, which has the potential to actually change the equilibrium concentrations of many of these constituents that are all connected in with these chemical reactions. Just a side remark, when you talk about geoengineering, and that's an emerging discussion now, unfortunately, stratospheric injection of aerosols to basically cool the planet. What you do by cooling the planet, we now know, we are heating the stratosphere again. And that heating of the stratosphere will be quite substantial. It will be actually throughout the entire stratosphere. And unlike nature, who also heats the stratosphere during volcanic eruptions, but only temporarily, because the atmosphere cleans itself on a time scale in the stratosphere of 2 to 3 years, geoengineering assumes that we will have continuous activity and injection, which means continuous change of the chemical equilibrium. That's really a blank spot in knowledge. People have started to simulate with these coupled chemical atmospheric circulation models that go up right into the upper stratosphere, the reaction of, or the response of chemical reactions to an injection of sulfate aerosols. So that's going a little bit adrift, but it's one of the questions to answer your question on, one of the issues to answer your question on what's next. What's next also is to know much more from the modeling side regarding impacts of climate change, impacts of extreme events in particular with regards to the water cycle in the atmosphere, so heavy precipitation, inundations, etc., is still not very well simulated in these global models. An interesting question that I find extremely urgent to respond to is what the monsoon systems do around the world, because these are the water providers for 1 billion people in the Indian subcontinent, for example. Does that react to climate change? How does it react? Does it become shorter? Is it shifted? Are there perhaps tipping points in this element of the climate system? We don't know. So these are sort of questions that are extremely important, but these questions are not fundamental to the questions, should we do something or not? They are more to prevent, to adapt, to help make decisions on a regional and local level.
Okay, more questions or comments?
Thank you very much. My question is whether there is an estimation of the amount of carbon dioxide that have been directly produced in the industrial area, so after the Industrial Revolution, and how, if so, how it compares with the observed increase of carbon dioxide, meaning did we stimulate secondary emissions besides what we directly emit with our activity?
Secondary emissions are, for example, when the ocean is heating up, the solubility is decreasing of carbon dioxide and some extra carbon dioxide is exhaled into the atmosphere. This is on the 1-digit % level. It's very, very small what comes from the ocean. What is probably bigger, but we don't know, is actually an additional sink by the terrestrial biosphere. So the vegetation takes up more carbon, but we don't know how permanent that uptake of carbon is due to the fertilization effect. We can estimate how big that is. It's an important service to the Earth and to humans, as important as the service that the ocean renders to us. If the ocean decided not to take up carbon dioxide, we would have a much higher concentration in the atmosphere and hence a much higher warming already by now. We would be way beyond 2 degrees Celsius by now. So there are a lot of important services and secondary effects. A third one is the permafrost in the high northern latitudes, which we all know is slowly melting. Some people say there is a tipping point, but it's been clear to me and many others that there is no tipping point there because the release of carbon that is stored in the permafrost is only so fast as the heat penetrates into the permafrost with the warming in the atmosphere and is able to melt the frozen ground. And that's a very slow process, and therefore the release of greenhouse gases, both methane and CO2, is relatively slow. It's sort of the same time scale as the warming, and there is no additional acceleration. What I haven't talked about is the entire measurements of carbon isotopes, both carbon-14, I've quickly mentioned, but not in that context, and carbon-13 foremost. With the burning of fossil fuel, we are emitting carbon dioxide into the atmosphere that is free of radiocarbon because we are burning an old source. And it's plant material, former plant material, that has a negative signature of carbon-13. So the carbon-13 concentration has decreased in the last 50 years. And that, together with the slow decrease of oxygen concentration and the increase of CO2 concentration, you can mix these three things together and then make quantitative estimates how much goes into the biosphere, how much is taken up by the ocean. And what is left in the atmosphere we can measure very precisely.
You started your talk with the search for the concentration of CO2 back in the past. And of course, there were some modulation, height and down, well before, let's say, the imprint of the human. Is it understood the mechanism of, let's say, rise and damping and more or less why that frequency is there? So what are the processes that are damping, let's say, in natural way, the CO2 in the climate?
Yeah. Well, in the ocean, so the question goes back to the time series over 8 glacial cycles, 800,000 years, and this rather clear variation between two seemingly hard limits. There aren't hard limits. We could imagine the glaciation being stronger. The big question, well, how was CO2 when there was perhaps even more ice on the planet? There are some physical processes that tell us that the ice sheets sitting on North America and on Greenland and Scandinavia cannot grow infinitely because they are mechanical features that are under stress, and therefore there is sort of an equilibrium and the maximum amount of ice that you can store. But we do know that the ice ages had a different character. I haven't shown you that. that would be a second lecture, a different character 800,000 years before today. If you go back about 1.5 million years, what used to be the 100,000 year high amplitude cycles that we have documented, before we had 40,000 year cycles, factor 2.5 faster, with about the same amount of glacial cooling, but much less warming during these cycles. And so a different character. And the big question there is, what did CO2 do? And that is the topic of our current European project, under the leadership, in fact, of a dear colleague from Tropospheric, where we drill an ice core that should go back, we don't know, should go back 1.5 million years, and where we then will measure carbon dioxide and methane. So yes, there could be surprises. I'm skeptical. There won't be too many surprises because we also have from marine sediments independent indicators how the level of carbon dioxide could have been. And we also have already, our US colleagues have analyzed recently, very, very old ice, up to 2.5 million year old ice that didn't show outrageous carbon dioxide concentrations. But what they lack is the continuous time axis that is sampled. They have individual samples of very old ice that comes to the surface close to the coastline due to the movement of the ice sheet. So, as to the processes, yes, I haven't really answered that. As to the processes, we are simulating with our models. However, you need coupled carbon cycle, biogeochemical, physical models to do that. We are simulating these ice age cycles, and we are able to more or less get the amplitude of about 100 ppm between glacial and interglacial.
One thing that was wondering me is that there is a very rapid increase and then a slow decrease. So
that's
I was wondering
this kind of a sawtooth pattern of the ice ages is sort of a very striking thing that was already discussed 50 years ago when people were analyzing marine sediments. Now it turns out that building up a terrestrial ice sheet, for example, on the North American continent or on Scandinavia, is a process that takes about 80,000 years. Because these are climate changes that are caused by the orbital elements of the Earth's position around the sun. It's the obliquity, it's the precession, it's the eccentricity. It's small changes on very slow timescales of 20,000, 40,000, and 100,000 years, plus the internal feedback processes, positive feedback processes. Now, it turns out it takes a long time, several tens of thousands of years, to build up the ice. But once it's warm and the ocean has warmed, it's eating away at these ice sheets. They can decay very rapidly within about 15,000 years. So the decay is much more rapid than the buildup of an ice sheet.
Atmosphere is a complex system, but it's also an heterogeneous system. And a difficulty in our model is represented by the aerosol. Can you increase the knowledge about the role of the aerosol, and can this knowledge improve the model for the
If I've understood you correctly, you are pointing towards the role of aerosols in, for example, the cloud formation. They also have a direct effect on the radiative balance, of course. And these two effects are heavily studied in laboratories, but also in the modeling where parametrizations and by now also machine learning is being used to come up with reasonable parametrizations of aerosol cloud water vapor interaction. So there is, yes, I agree, still a lot to be learned. The question, for example, how big is really the radiative cooling that we have experienced in the last 50 years? In the last 2 years, there are colleagues who say, because of cleaner ship fuel, there has been an emission reduction in aerosols, and therefore this compounds to the current record warming that we have experienced and measured in the last 15 months. You remember, perhaps you're aware of this ongoing discussion. Why has 2023 and 24 up to now been so hot? Hotter than any other year on measurement. And just to give you an example, the global ocean surface temperature between 60 south and 60 north around the globe is warmer in 2023 and 24 than ever observed since the 1980s. And scientists, of course, debate, and aerosol is one of the potential mechanisms that explain that. Yeah, exactly. So yes, it's still an area of intense research. We have in Switzerland at ETH, there is a colleague, she actually does measurements in situ with balloons, etc., where she tries to investigate how clouds react to different concentrations and different species of aerosols that are injected. Right.
Good afternoon, and I'm here.
Ah, okay. Yeah.
And thank you for the insightful conference. I wanted to ask if the present measures taken to decrease climate change would be actually applied, what temperature increase will be reached? It will be the 2 degrees or less or more?
Well, unfortunately, there are no measures yet being taken to be serious. The emissions of greenhouse gases only see one direction, and that is upward. What we have not yet on a global scale managed to do is to bend this curve of emissions and to reach or to not go beyond the 1.5 or the 2.5, the 1.5 or the 2 degree warming limit that is in the Paris Agreement. We would have to come down with the global emissions by 2050 at least 50%. And then from then onwards down to even negative, because on the long run, between now and 2050, we will have already emitted too much for 2 degrees, so we need negative emissions. But unfortunately, I don't see any global effort here, apart from the negotiations and the regular conference of the parties towards every end of every year. These concentrations have gone upward, our highest ever, and we really don't see a transition to a fossil fuel-free world. Now, this sounds very negative. I should end my response with something positive. We also have seen that PV, which is an essential element of the renewable energy mix, has decreased in price per kilowatt tremendously, factor of 100 to 1,000 compared to 20 years ago. So it's to hope that this technology now will be affordable at scale, which then leads to a distribution of energy sources. Energy will be harvested where it's used, but that opens up a new challenge on distribution of energy. Our energy distribution of electricity is based on the principle of a few producers of energy that distribute that energy and not a distributed network of producers. And that has to change, that will hopefully change, and I'm on that front quite optimistic that PV and heat pumps, another physical great thing, the Carnot cycle, if you use a heat pump, In my house, I have a factor of 5 for every kilowatt of electricity that I buy. I get 5 kilowatts of heat to heat my house. That's great. That's the heat pump. That's why it's called the heat pump. And so there is hope there, but there is no way around also our pattern of consumption. There's no way around circular economy. Don't be afraid of circular economy. That's not something from revolutionary or something. It's the most useful thing to think of because the planet is finite. And so all our resources are finite. A geologist or a geochemist recently told me that if I collect all your mobile phones and we put them on a heap, this has a density of minerals and of rare earths and of metals that is about 20 times higher than any producing mine on this planet. And yet it's not harvested. And yet we still have labor conditions to pull out these raw materials and these resources under dire conditions, under dire human conditions, if we could actually extract them from our waste. That's the way to go, and that's what people should do. Anyways, I'm rambling along.
Thanks a lot. I'm very curious, are there feedback effects which could imply a not linear or even exponential increase of the temperature of carbon dioxide emission?
Of course, scientists have speculated that this could happen, like at Venus. The key word is a runaway greenhouse effect, but that's fantasy land. Quite seriously, I must say, the Planck feedback, this lambda that I've shown you that is fortunately negative, is so strong. The Planck's law is such a robust law, and that lambda in Planck is fortunately negative because we are losing the energy to space, so that's a negative sign, and that stabilizes the climate system. So for planet Earth, I'm quite convinced that there is no runaway greenhouse effect. There are other nonlinearities that could actually be a spoiler, not to the global mean temperature, but for example to sea level rise. You've probably heard about the instability of the West Antarctic ice sheet that may be close to a tipping point, and that's something that is of concern, that the warming that is going on could destabilize parts of Antarctica that then would flow away, give way to the inland glacier flow, and bring substantial amount of ice into the ocean, which melts and adds to sea level. But sea level would rise slowly, but the really dangerous thing is that your adaptation measures that you have taken for, say, 1 meter sea level rise extra are no longer valid. They may actually require to be 2 or 3 meters. And so that is a real question and challenge. Something I didn't know, for example, I always thought Holland is in a good situation. They know the technology, they know how to build dikes and so forth. But they know precisely that there is actually a limit of a dike height. Because if the dike is too high, you cannot simply add a meter of dike, because that adds a lot of material and the whole thing sinks down. Okay, I didn't think about that. But they are not built on rock in Holland. It's sort of, rubble and soil. And anyway, so there are limits, and there are surprises in the climate system. There are nonlinear effects, but I don't think the greenhouse gas, the global greenhouse effect, has the potential to be runaway here.
Was there a question up there? Yes.
Thank you for the talk. I have more of a curiosity than a question. I would like to touch again on the extreme meteorological events. And there was, I mean, you explained that
you hold the microphone a bit better.
Sorry. Okay.
Like a movie star.
Okay.
Or a music star.
Yeah, earlier you talked about the probability of such events, but I was wondering, can you also, well, understand spatially, geographically, how these events can be distributed? I mean, if, well, bottom line, if some world areas are more at risk than others, or if it's in order.
For heat waves, it's not very difficult because heat waves, and the results are quite robust, because heat waves are essentially a thermodynamic feature of the atmosphere. But when it comes to inundation or heavy precipitation, it becomes difficult. And so there we cannot with great confidence say, oh, this area will be affected 50% more than the other area in a different region of the country. Drought is another thing. Drought is actually quite robust as well, as long as some precipitation effects that would replenish groundwater reservoirs do not kick in. For example, in Spain, all the current climate models are predicting for all scenarios towards the end of the 21st century a massive drying. In fact, the entire Mediterranean area undergoes a massive drying. I do think that this is a robust result. And so on that granularity, Mediterranean area versus Switzerland, north of the Alps, we are quite fortunate. What our problem in climate change is the seasonality of precipitation. We get over the year under global warming almost the same amount of water, but we get a lot more water in winter and we don't get the snow anymore. So tourism, etc., you can imagine. And we dry out in the summer. So the hydrological or the seasonal cycle of precipitation that used to be like this will become like this. And the reason is we lose our glaciers at a massive velocity, at a massive speed. And so these things can be modeled today quite faithfully, but the most difficult thing, and these are the hurricanes and the circulation changes in the atmosphere. There we're not blind, but we know very little because, as you say, the atmosphere is very complicated. And for example, the hurricanes, you know that a hurricane needs about 27 degrees of surface water temperature to start growing. And so it's very trivial to say, okay, in global warming, the area of 27 and hotter at sea surface temperature will become bigger, of course. So the likelihood of having a hurricane developing is bigger, so more hurricanes. Yes, that's true. But the hurricane life cycle is also determined by the vertical temperature gradient. And that is also changing somewhat. The stability of the atmosphere is precisely there where the hurricane is building, and so that is a compensating effect, and the net sum, to project the net sum is extremely difficult. That's why you don't find in IPCC definite statements about how hurricane strength will actually develop in the next 50 years.
Okay, more questions or comments? Okay, I don't see any more, but I would like to ask you for a last take-home message for today. Yes. So
very short. Climate is
IPCC report made a very clear statement regarding the connection between the dramatic change in the dramatic increase in the concentration of CO2 with the human activities, and asks quests for political actions. Nevertheless, and the plot that you showed us at the beginning, I think is very self-explanatory. But nevertheless, there are communities that seem to have a hard time acknowledging the anthropogenic nature of this dramatic change. So what is your take-home message for those communities?
Well, listen to the science. I cannot say anything else. Listen to the science. Be very critical to the sources of information. Unfortunately, today, everybody can generate information. Even machines nowadays can generate information. But not every information is factual. What I can assure you is that if you read these pages of the IPCC report, and you can now tell me, oh, I can't read 1,500 pages because they are so thick, and I agree with you, but there are summaries that are only 20 pages, and there are headlines, one of them I showed you, they print on 2 pages. Read that, and that is the state of knowledge of the science, and not something in a blog, and not something on a web page, and not something that a colleague of you who says he is a so-and-so scientist, not naming names, I've heard that, or, oh, I've done my whole life physics and I know climate is not changing. You respond, climate change is physics. Thank you very much. Thank you. No, it's still here. Still here. Thank you very much.
Thank you very much.